Determine the forces in each member of the space truss. State if the members are in tension or compression. Supports at A and B are rollers, and C is a ball and socket. Is this truss stable? To determine the stability of this truss, we need to use our formula B plus R, which is basically the number of members plus their action forces, and then 3 times the number of joints. In this case, we have 9 members, and then we have 5 reactions, 1 at each rollers, and then 3 at the joint C. And now 3 times joints, so we have 5 joints, so 5 times 3 is 15. In this case, you're going to have a total of 14 bars and joints, and 15 is our 3 times joints, which is basically 3 equilibrium equations for each joint. In this case, our truss is unstable, but we can still solve for this. To begin, you need to realize that this truss is symmetric. This means that our action forces at A and BZ are going to be same, and there are going to be some more forces in the members that are going to be symmetric, which we will discuss as we progress through this problem. Looking at this whole truss, we know that we're not going to have any reactions in the X and Y at joint C, and there's only going to be one reaction in Z axis. Now let's take a moment about the point C to find our solution for AZ and BZ, or external reaction forces. And we have already determined that our AZ is going to be equal to BZ. So therefore, in our equilibrium equation, we're going to write 2 times AZ, and then it's 3 feet. Both of them are 3 feet away from our joint C in the X direction. Then we have negative 8K, and it's 7 feet away, all equals to 0. All for AZ and BZ, we get our solution as 9.33K upwards. Now we can sum the forces in Z direction. So when we sum the forces in the Z direction, we can have negative CZ positive 2 times 9.33K, and then negative 8K, all equals to 0. Solve for CZ, we get a solution as 10.66K. And rounding it up, it would become 10.67K. And we have already said our Cy is going to be 0, and our Cx is going to be 0 as well. Now that we have our external reaction forces, let's start solving for forces in the members. We can start with joint E. So at joint E, we have our 8K, and it's projecting in only Z axis. Then we have, I use this method of highlighting each force vector with its projection along whichever axis it is acting on. so that it's easier when we are creating our equilibrium equations. And then we have our force DE along y-axis, and it's unknown. Then we have our force EA, and it's projecting along X and Z axis. And then we have EB and it's projecting along Y and Z. Oh, then we have missed one point here because our joint E is moving, and I was looking at joint B when I was explaining the projections. So our E and A is projecting along all three planes, and so is EB. Now, to solve this problem, we have to also realize here that reaction in force member AE and B are same. Similarly, at joint D, we're going to have force AD and BD similar or same. And finally, at joint C, we're going to have force AC, which is going to be same as force CB. Okay, and now to continue, let's sum the forces in Z direction at point E or joint E. We're going to have negative 8K. Then we're going to have Z component of EA and EA and EB, and it's going to be positive. But we're going to take a shortcut here. We're going to times it 2, and because we have already said that AE and BE are same, this means we're just going to times it twice and use one of the forces, either A or BE, and times its Z component, which in this case is going to be 8 divided by the square root of 3 squared plus 4 squared plus 8 squared is square root of 89, all equals to 0. Solving for A, get our solution as 4.72K. Now, since it's positive, this also tells us that this member is in compression. Now we can sum the forces in X direction, Y direction. So we're going to have positive force DE, and then Y component of EB and EA, in other words, BE and AE. Both are positive, and because both are similar, we're going to have 2 times 7.2K times 4 square root of 89, all equals to 0. and solve for DE, we get our solution as negative 4 kilonewton. This means we assumed our vector direction in the wrong direction. Switching it over, we get our solution in the positive and also tell us that this member is in tension. Now we have solved all the direction or forces in the members for joint E, we can proceed to our next joint. We're going to start with joint C. At joint C, we have our CZ, which we found to be 10.67 K. Then we have our action, our force, unknown force, DC, and we have our unknowns, CB and CA. And let's talk about the projections. So force DC only projects in X and Z axis, pardon me, X and Y, or Y and Z. And then CB is only projecting in X and Y axis. So is CA. To begin, let's sum the forces in Z direction. Going to have negative 10.67 K, and then Z component of force DC all equals to 0, and we get our solution for force DC as 11.39 K. We can sum the forces in X or Y direction, doesn't really matter. We're gonna have, pardon me, it does matter because force DC only projects in Y and Z direction, therefore we'll have to sum the forces in Y direction. That means we can have Y component of the force DC, and then we can have Y component of CB and CA because they are one and same. We're gonna have negative 2 times unknown force CB or CA times the X component or the, pardon me, the Y component of both of these. We get our solution as 2.828 K, or rounding it up, we get 2.83 K. And since our solution is in positive and looking at our vector direction, we know that this member is in compression and so is member CA. So now we have our DE found, EA found, and EB found. We have DC found, CB found, CF found. Okay. So now find our remaining. Let's take free body diagram of joint D. So let's see, we're gonna have our DE, which we found to be 4 kilonewton. Now let's project in Y axis only. Then we have our DC, which is projecting in Y and Z. And we found it to be 11.39 K. Then we have our another projection of unknown force DA, and it's projecting in along X-axis and Z-axis. And then finally we have our DB, which is projecting along Y, and Z. Alright, to begin, we can begin along Z or Y axis, but it'll be easier if we do it along Z axis. Reason being, there's only one known vector that's projecting in Z direction. Therefore, it'll be a little bit easier to solve. Alright, so now we're going to have our force from vector DC, which is 11.39k, and we're going to need the Z component of this vector. And it's 8 divided by 8.54. And then similarly, we're going to have Z component for dB and dA. And we have already said, because of the symmetry, they are one and the same. Therefore, we're going to have 2 times either force dA or dB, and then the Z component. And one thing I just noticed while I was solving for our equilibrium equation, that I said our force dB is projecting along Y and Z, but in fact it's projecting along X and Z. Okay, continuing with our equilibrium equation, solving for force dA, we get our solution as 5.695K, and both of these are in compression. Now finally, we can draw our joint A. We're going to have our known force dA projecting along Y and Z, pardon me, X and Z. And we have our force EA as projecting along X, Y, Z. Pardon me, it's not projecting along, or is it? It is, my bad. It is projecting along X, Y, Z. And then finally we have our force CA projecting along X and Y. And finally we have our unknown force AB projecting only along X-axis. Now to solve this problem, you just have to sum the forces in X direction. We're going to have force AB